Okay, here's another example from section 3.1, and this is dealing with piecewise functions. And we have a piecewise function here, f of x, defined as x minus x squared when x is less than or equal to 1, and 3x when x is greater than 1. And we can actually just break this up and say when x is less than 1, it's equal to this, and when x is equal to 1, it's also equal to x minus x squared. So that's going to maybe help if we differentiate that. And the question is, does f of x have a derivative at x equals 1? Now remember, a derivative is a limit. We have left-hand limits and right-hand limits, so in order for the that limit to exist, the left-hand limit must equal the right-hand limit, so the left-hand derivative must equal the right-hand derivative. Or the slope from the left must equal the slope from the right in order for the derivative to exist at a point. So that's what we want to test. So we're going to use our definition of a derivative at a point. So we'll start with our left-hand derivative. Or our left-hand limit, because the derivative is a limit, and that's going to be equal to the limit as h approaches 0 from the left. In other words, our h is going to get smaller and smaller, of f of a plus h minus f of a all over h. All right? And then we can substitute, so that's going to equal the limit as h approaches 0 from the left of my function. And my a is going to be 1, so we're examining what's happening at the point 1. So f of 1 plus h minus f of 1 all over h. So we're going to go back and put the a in, and the a is 1. Now let's look at this. Now remember, as h approaches 0 from the left, if we look at our number line here, and here's 0, these numbers here are negative, these numbers here are positive. So as h approaches 0 from the left, you can see that there, then h is going to be negative. All right? So if I add a negative to 1, this is going to make this number less than 1. And f of 1 is no problem. That's equal to 1, so we don't have a problem there. So when it's less than 1, and in this case, this number in here, this is the x, not the whole value. So this x is going to be less than 1. In this case, the x equals 1. So that tells me which functions I'm going to use, because the functions are defined for values of x. So since x is less than 1, I'm going to use this function. And since x is equal to 1, I'm going to use this function again. So that's what I'm going to put in. So it's going to be something minus something squared. And this is going to be 1 plus h. So it's going to be 1 plus h minus 1 plus h squared. And then minus, and then I'll put 1 in here. Okay, so it's going to be 1. So I'll put a bracket here, and it's going to be 1 minus 1 squared. It's going to all be over h. And when these fraction bars get long, I like to use a ruler. All over h. Okay, so we're using this function here because my 1 plus h is going to be less than 1 because h is negative. So I'm going to use this and this, all right? So something minus something squared, minus, and I'm going to put 1 in here, so 1 minus 1 squared. Okay, and this is going to be 1 plus h, and then if I square this out, this is going to be, and I can maybe do it over here just to save some time, if I square this, it's going to be 1 plus 2h plus h squared, right? If I square that. And then if I precede it by a negative sign, it's going to be negative 1, negative 2h, negative h squared. All right? And over here, this is going to be minus, and then 1 minus 1 squared is 0, so that's nice. all over h. And we can simplify this as the limit as h approaches 0 from the negative direction. Oops, let me move this out of the way here. And 1 minus 1 goes away. So I've got a 1 minus 2h is negative h. So I've got negative h and negative h squared. All over h. Now if I take that limit, I still have 0 over 0, but I can simplify that. So that's going to equal of negative, I'll just factor out a negative h times 1 minus h. I'm sorry, 1 plus h, I took out a negative. All over h. And those h's become 1, so I've got equals the limit as h approaches 0 from the negative direction. Oops, running out of room here, pardon me. There we go. And that's just going to be negative 1 plus h. And now I can simplify, and that's just going to be negative 1 plus 0, and that's just going to be negative 1. So there's my slope there. So that's my left-hand derivative, negative 1. Now we can do the right-hand derivative, but I think you can see that since it's a line, it's going to be 3, but we just go through the formalization of this. So we're going to take the right-hand derivative. So that's going to be the limit as h approaches 0 from the positive direction. Just up here a little bit higher. And I could use my same definition as above, and then it's going to, so I just substitute, so that's going to be f of 1 plus h minus f of 1. So it looks like the same thing, right? All over h. Except now, as we approach h from the positive direction, if you go back up here and look at our little number line, as we approach h from the positive direction, it's going to be positive number. So if I add a positive number to 1, it's going to be greater than 1. But in this case, it's still going to be equal to 1. All right? Oops, we're down here. So since this is h is going to be greater than 0, I'm adding a something to 1, so it's going to be bigger than 1. And this is still equal to 1. So in this case, I'm going to use this function, 3x. But in this case, I'm going to use my original function, or my first function, x squared minus x minus x squared, because x equals 1. So you have to put those in the appropriate functions. All right? So this equals the limit as h approaches 0 from the positive direction. Okay? And I'm going to use 3 times something, so that's going to be 3 times x. In this case, the x is 1 plus h. Okay? But then minus the same thing we had, because that's the f of 1. So I'm using the first part, so we're using this part again, but this is the new part because they're going to be greater than 1. We're still using the equal to 1 because that hasn't changed. Okay? So if that makes sense. All right? So that's going to be 1 minus 1 squared. And that's going to be all over h. So that's going to equal the limit as h approaches 0 from the positive direction. And this is just going to be 3 plus h. This is a little bit easier to work out. Excuse me, 3 plus 3h. Minus 0 all over h. And then I can break this up. Now 0 just goes away. So I've got 3, but I can't factor out an h, see, so I've got a kind of a dilemma here. So what I'll do is I'll break this up. Because normally we could factor out an h and we get some kind of simplification, some kind of satisfaction here. Okay. Okay, so as I do this, I end up with a limit, and we're just talking about the derivative at this junction point, so this is where the issue is, all right? So we have the limit as h approaches 0 from the positive direction, and part of it's okay, that's just going to be 3 over h, we'll break it up, plus the limit as h approaches 0 from the positive direction of 3h over h. Okay, so I have 3 over h plus 3h over h. All right, does everybody see that? So you can break that up. 3 over h plus 3h over h. Okay, now this is just going to be 3, so that's what we were talking about when we talked about the fact that we would get a derivative of 3, but we're talking about this right-hand derivative, not just the derivative of the function. So this is where we have an issue. Three over h plus the limit as h approaches 0 from the positive direction of 3. Well, that's just going to be 3, so that's no problem. But what's this going to be? Well, as this gets very, very small, we've got 3 over a very, very small number. So this is like an asymptote, so this is going to be approaching infinity. So this is going to be equal to three times 1 over, and we can think of this as a very, very, very small number because it's approaching h from the positive direction, so a very, very small positive number. And this limit is 3. Well, this is going to be equal to, and this is 1 over very small numbers, is going to be infinity. So we've got 3 times infinity plus 3, which is really infinity plus 3, which is infinity, and that means the limit does not exist. So our right-hand derivative does not exist. Our left-hand derivative does exist, so since they're not the same, obviously, and if the right-hand derivative doesn't exist, then you're pretty much done anyway. So if I would have done this first, I would have known I don't have a derivative there. So if that's the case, then f of x does not have a derivative at x equals 1. Okay? And again, what I did was I just broke this up, so I kind of skipped a step, but we know that 3 plus 3h over h equals 3 over h plus 3h over h, right? We just put them over common denominators. So we know that. So all I did was break that up. And then I said the limit of a sum is the sum of the limits. So I just broke that up. Okay? So I hope that makes sense.